story ever told.
Hello everyone, I'm Radu. Welcome to Swift Nuggets. Today is 30th of April. Plan is to see what happened lately in Swift, check latest proposals, the new Xcode, new things that were added into the Swift language. So welcome, sit back and enjoy. First, since we last spoke, we are now at Xcode 16.3, was released at the end of March, and it ships with Swift 6.1 language. The Swift team added quite a longer list of features. They resolved a few issues here. They fixed a crash that sometimes occurs when fetching variables or running Swift expressions, for example. Some LLDB improvements, more like a bunch of simulator issues, some issues with command keys. They no longer discard key up events for keys when the command key is held. There were some problems when people tried to download iPhone 16e simulator. Now it's fixed. There were also some issues where you could download the simulator runtime, but it was not usable in Xcode and a lot of other improvements to Swift. And yesterday or a couple of days ago released the Xcode 16.4 beta 1 version. It doesn't say much, but it ships with iOS 18.5 and it resolved one Apple client compiler issue related to traits. It was a problem in Xcode 16.3, and there was some improvements and things. There is a new feature, device CTL diagnose now obtains a sysdiagnose from your Mac and all available devices by default. So I expect more betas to come, but we'll see how Apple plays it out. Xcode 16.4 ships with Swift 6.1.2 compiler, and as I mentioned, it brings up the SDK for iOS 18.5. Last time in first episode we gone through a lot of proposals. Most of them were adopted in Swift 6.1, and we discussed a few of them to be added in future Swift proposals. And now some of those future Swift proposals have been added to Swift 6.2, such as non-escapable types, also span and row identifiers, integer generic parameters, inline array, fixed size array, and the safety checks about the strict memory things. That there are also a few proposals which we haven't discussed in the previous episode but were added in Swift 6.2. We have here like 5 of them: task priority escalation APIs. We'll see together what it is. Of course, the next ones as well: Objective-C completion handler, parameter as sendable, naming tasks, control default actor isolation inference, and the global actor isolated conformance. So some multi-thread things and Swift concurrency parts. And we have new proposals which are intended to be added in a future Swift version. We have explicit specialization, run non-isolated async functions on the colors actor by default, UTF-8 span, safe UTF-8 processing over contiguous bytes. Some things about the standard library primitives, adding non-escapable capability to those, adding mutable span and mutable row span, and 2 others like hashable conformance for async and throwing async string continuation, and finally the clock epochs. All right, so let's dive in. A short refresher on non-escapable types. I know like a bit difficult to comprehend, especially if you're not using in real projects into your like work projects, but I think it's still a nice topic to discuss and to learn. Escapable, non-escapable is now part of Swift 6.2. It was added as part of the proposal 0446. It complements the non-copyable. We have now a new type constraint called non-escapable with tilde, and it's used for types that can be locally copied but cannot be assigned or transferred outside of their immediate scope. We already have something like that. We have those closures which are like escaping and non-escaping, if you remember, but with this proposal it's now type and you can adopt it to your structures. For classes and actors it's not going to work, and this complements the non-copyable types which were added with Swift proposal 390, and introduces another set of compile time enforced lifetime controls for safe, highly performant APIs. It's a necessary requirement to be added for a thing called span. We'll see in a minute what it's span. And in the proposal, it's describing why it was needed. We have the example of an iterator which has several weaknesses. It can have a negative constraint on performance, such as a reference counting overhead. You have standard library iterators which store reference counted pointers to ensure safety. And this produces some kind of runtime overhead. And a few limitations for the embedded systems. For them, the reference counting makes these types unusable in highly constrained embedded environments. Right. So, as I mentioned in the last episode, the purpose for non-escapable is to prevent a type from being used outside its immediate context. Values can be copied locally, but cannot escape their scope. That's simple as that. For types that need to maintain lifetime constraint relative to other data, that can be a possible use case. But attention, to not think that non-escapable is the same as non-copyable. The variable that you use, it gets consumed. If you like access something from it or you assign it to another variable, then the initial variable gets consumed. You cannot use it anymore. While the non-escapable part, you can copy that variable within the local scope. That's important to understand. Non-copyable can't be used anywhere if you pass it by reference, but non-escapable cannot escape the immediate context. All right, so all Swift types are implicitly escapable by default, where like if you add a non-escapable thing to a structure, it will become like non-escapable, but for the others, it is marked as escapable. The exception are the non-escapable closures. There are also some restrictions and some constraints for non-escapable. You cannot assign them to a global variable or a variable in a larger scope. You cannot return that non-escapable variable from the current scope, and you cannot store that in a global variable. Right? I have here a small in the video. If you watch the podcast, I'm like having a demo project in Swift and trying to create a refresher for non-copyable types protocol. And this was introduced as part of Swift evolution proposal 390, where like structs and enums cannot be copied. It's applied to structures and enums, and you used it to like mark the non-copyability of them. So we can create here a structure called greeting, and we can say tilde copyable, and my structure will become non-copyable. And if I say here, I declare a variable, say hello variable, which is a string, it's totally fine. I will try the same greeting non-escapable and adhere it to escapable protocol. I cannot declare here a variable which is a string because this one needs to become escapable as well. We can apply like generics and say if t is non-escapable, then we can use t here. In like say hello var, now it becomes a generic which is non-escapable. Anyways, to enable non-escapability, if you have like Xcode 16.3, which doesn't get shipped with Swift 6.2, you need to enable a flag. You should go to the build settings of your target or your project and go to other Swift flags, and you have dash enable experimental feature, and you could add the parameter lifetime dependence. And in this way, you can play with like non-escapable addition to the language. Right. So if you remember a greeting which is like non-copyable, and let's create here a function. I'm inside of a Swift UI view, the classic content view, and let's say declare a function. Let's say hello. We can declare here, let greeting equal greeting. Say hello variable. I put hello here. And if I assign it to a new variable, such I copy it. Another greeting equals my initial greeting. It's totally fine. And I can reference that property, greeting dot say hello variable, and it will work. And if I assign it to another greeting and then I will print another greeting, say hello variable, it will simply work and compile, everything is fine. But if I use the initial variables, say hello variable, I calling that variable from the initial variable that I declared that previously, it won't let me. The compiler will get me an error saying that, hey, this variable has been consumed already. And now it comes the new part where you add the consuming and the borrowing parameters, which are like special keywords. And you can create a function where you like say hello again. And here you could pass the greeting. And you could say, let's borrow it using the borrowing keyword for my greeting. And if I borrow it, then I could say print and everything is fine. But if I place consuming, then that variable will get consumed. Then that's a refresher on the copyable, non-copyable parts. For the non-escapable, we can create another variable, greeting non-escapable, and we can do whatever we want here. So we can assign it to another variable, but we cannot return this. It will get like outside of the scope, and we would get an error, cannot infer lifetime dependence on a self, which is bytewise copyable and escapable. Basically saying, oh, okay, this non-escapable variable cannot leave this scope. All right, and it doesn't work if you declare a global variable or a variable here inside the contiguous structure as a non-escapable and you try to assign it to that variable, it won't work. It's not permitted. You have some examples in the Swift proposal where you could like borrow the not escapable variable inside other functions, so you can totally make it work like that, but it should not leave the scope it's currently living in. Very important to remember that classes and actors cannot be declared non-escapable. Some practical application you might think of where you can use non-escapable. You can think about iterators. They ensure they don't outlive their source data. Views into data, like you look at some data, like a buffer, whatever. And similar with what we'll be discussing next, the span. You look inside of the data, but you cannot escape the context that that data is found. Right. And the both are needed because non-copyable alone wasn't sufficient for the span type. And that's because we have different constraints and it keeps like the protocols concentrated on two things. Non-copyable prevents duplication, while non-escapable prevents escaping the scope. And these are like quite flexible and are not linked between them. They are like separate concepts and you should think about them. Which brings me to the next Swift proposal, the span part, which is a safe access to contiguous storage. First, to the fact that the memory zone where the data is being stored is in an uninterrupted manner is a sequential bytes, a series of bytes which are there, and you know it's there. Swift spans are being introduced as part of Swift proposal 447 and are already shipped with Swift 6.2. Whenever that will come up, we'll also include the span types. Right. And this is a new abstraction for container agnostic access to contiguous memory in Swift. This feature allows you to safely share and access that part of memory across different containers without having like leaks of memory, or you have like unsafe part where you access the memory in an unsafe way. You have spatial safety, the initialization is fine, and it also brings a safety to the types. Before span, we had the lack of safety when we wanted to access a part of a memory, and it also very inefficient. There was not like some kind of a performance benefit when you try to do that. Consider a scenario where you have data in one format, like integers, unsigned integers, or data from foundation or string, but you need to process it within a library that expects a different format of that. You'd probably use some kind of a opaque generic function like some sequence of unsigned integers 8 or the unsafe pointer, unsafe buffer pointer, and you need to declare the type. And the pointer itself is unmanaged, it's unsafe, and it could produce some problems there. And here we go, you have span, which is like a safe, reliant, performant alternative that combines the best of those approaches, and it offers you a view, a window inside that zone of memory. You cannot copy the data, which you see there. You can provide a borrowed view for that zone of memory, and the span cannot escape its context. It relies on the guarantee that the original container cannot be modified or destroyed. It also performs bounds checking. What that does it mean? It means that every access is bounds checked to preserve the spatial safety I was talking about. And it always represents the initialized memory. It preserves the definite initialization guarantee. Cool. What's cool about span is like it's container agnostic access. It doesn't care what's there. You can have a way to access the internal representation of any type that provides it, regardless of the container type. This means you can write functions that work with any container that can provide a span. And I mentioned like it's bounds checked, so you have the spatial safety, and it doesn't copy the data that you see there. It's very efficient for large data sets. Okay, cool. So why do we need span? Right now in Swift, if you want to work with data in different formats, you have two options. You have the unsafe pointers and the generic functions. Well, span gives you the best of both worlds. It's both flexible and fast, while it's still being considered safe. Span, think about it, is, as I mentioned, a window or a view into a piece of data. You see the data, but you cannot copy it. You can store or return it. It must stay inside the context that it was read. And it works with any kind of a container, any type of container, like arrays, strings, data objects, and etc. And it ensures that the memory is valid. And you have here in the proposal quite some good examples, and also the future directions, which is an essential part of the memory safety that the team, the Swift team, is bringing to the language. And I suggest you go through the proposal, which is quite large. Right, row identifiers, which were added as well to 6.2 as part of 451 proposal. If you remember from last time, you had those backticks characters that you could use for escaping some keywords, some parts, some functions, and so on. And now but it didn't work for like enums and so on. And now we have more flexibility with adding backticks. You could like put cases with integers and so on. I won't go into details. If you want to check the escaped identifiers, please check it from the previous episode. Cool. At 452 integer generic parameters, you could or it solves the problem where you didn't have a fixed size or fixed capacity collections with the inline storage. We could repeat the elements when declaring an array, but now with this integer generic parameters proposal, we're now having a way to provide the number of elements of that array, for example. InlineArray, a fixed size array, which was added as part of 453 into Swift 6.2, and is a new type that gives you a fixed size array that lives on the stack, not on the heap, and can grow or shrink. Is more efficient than regular arrays. What kind of problem it solves is like the regular array can grow or shrink, but always use the heap memory to be stored. And if you use tuples, you have a fixed size, but hard to work with. Cannot use loops or indexing, for example. While inline arrays gives you a better option when you know exactly how many items you need. And finally, Swift proposal 458, opt-in strict memory safety checking, which was presented in the last episode as well, is a more thorough proposal. It has very good documentation here, and it describes the process, the vision that the Swift team has for the memory safety. Strict memory safety is a new feature that will help us write safer code. It has three key ideas for it, like finds the potential problems, identifies the places where your code might be unsafe, make some decisions about that, like forces you to explicitly acknowledge when you're using unsafe feature. Think about like the sendable with unchecked. You can like unchecked sendable, and improves the code quality, suggesting probably through warnings in the compiler safer alternatives when available. Here we have the properties of how can we declare a memory safe, and it were bounded into the Swift language. You have the lifetime safety, the bound safety, also the type safety, initialization safety, and thread safety, all of them being addressed by Swift. But since its inception, Swift has provided a memory safety for the first 4 dimensions. And Swift does that through a mixture of static and dynamic checks. Static checks are better, of course, because they are like shown at compile time, while the others are not shown, and you could produce like crashes when you run the program. Swift offers unsafe features to allow problems to be solved when neither static nor dynamic checks are sufficient. For example, you have here in the proposal, you have the null references with optional type. And statically, Swift prevents you from using an optional reference without checking it first. If you're sure it's not null, you can use the exclamation operator, which is safe because Swift will dynamically check for nil. If you really can't afford that dynamic check, you can use the unsafe wrap. This can still be correct if you can prove that the reference is not null for some reason that Swift doesn't know, but it's an unsafe feature because it admits violation if you're wrong. So if you use the exclamation point and you're wrong, then all right, you have a crash and the program will stop. And with this proposal, you have an opt-in, very important to remember, strict memory safety checking mode that identifies all uses of unsafe behavior within the given model. I have a compiler flag, an attribute at unsafe, also at safe, and some other additions. So with strict memory check, you add this at unsafe, and this indicates that the structure is unsafe. For example, the unsafe buffer pointer here in the example. You could also have a function which like takes as a closure with unsafe buffer pointer, and here in the closure it gives you a warning, use unsafe function and unsafe property. All right, so you have these keywords, the functions, and so on. You directly can use unsafe keyword and mark it there. When you should use it, if you want to make your code more secure, so it's opt-in. If you're working on a project where safety is critical, you want to identify potential memory safety issues, or you're learning Swift and want to avoid unsafe patterns. In simple terms, think of strict memory safety as a safety inspector that points out potential dangerous code, suggests safer ways to do things, or helps even to create like a reliable code. It's like having a safety expert looking over your shoulder, helping you to write better and safer code. Right, and with 4.6.2 task priority escalation APIs added in Swift 6.2, we have a new addition and introducer to the Swift concurrency APIs. And with this, you handle the task priority escalation in the concurrency system. Think of this priority thing like a priority inheritance system where tasks can inherit like higher priorities from their parents to prevent like priority inversion problems and so on. You have the automatic priority escalation. So Swift already automatically escalates priorities in structured concurrency. When a high priority task awaits a lower priority task, the lower task and its children get priority boosts. You have a new API with task priority escalation handler called, and reacts to the priority changes. But you can also use task from Swift concurrency, and you have a new function escalate priority. So you define a parent task, for example. You then declare a child task within the parent task, and you need to await for the child task to complete. If a high priority task waits this, the both parent and child priority will boost. You could declare it as part of a handler. Define let task equal task, and then you declare what you do inside that task. And inside of the body, you could say like await task priority escalation handler, do some work, like wait for some work to finish, and you could you have a new closure on priority escalated and gives you a new priority, and inside the new priority you can do something there. This is very useful if you want, like, you're working on a performance or critical application where you need to boost the priority and you need to coordinate the task priorities, also libraries that need to react to priority changes, maybe scenarios where priority inversion could cause like performance issues. The key benefit is that it provides a way to ensure that high priority work doesn't get stuck or waits for something else to finish, while you maintain the structured concurrency model that we have it from Swift 6. Next one, import Objective-C completion handler parameters as Sendable, implemented in Swift 6.2. And this proposal basically changes the Objective-C importing rules such that completion handler parameters are sendable by default. So we get that for Objective-C functions parameter, we have them now sendable by default. We could also opt out for the sendable completion handlers with like add non-sendable here. Well, this proposal is a great thing. Now, whenever like we Swift call functions from Objective-C, we now have completion handlers ensured that the data race safety is happening inside the concurrency boundaries. We have the data race safety model where like you require explicit declaration of concurrency, probably in variants and so on. And if you remember, sendable is like number one thing that serves as a type level guarantee that the value can be safely passed across different concurrency boundaries. Another one about the concurrency thing, control default actor isolation inference added in 4.6.6, and it's already implemented in Swift 6.2. We have a new setting, a compiler setting for inferring main actor isolation by default within the module to mitigate false positive data array safety errors in the code. Note that the code is running sequential and we are not using inside of a concurrency model, but the compiler for some reason treated as a concurrent by default. Like whenever we declare something there, it created some kind of a problem, a theoretical false positive in the type system. Now the proposal changes the default isolation of the domain. You could specify the default isolation per module using a compiler flag called default isolation, like default actor isolation inference. When the default actor isolation is specified as main actor, declarations are inferred to be at main actor isolated by default. Task naming, the proposal 4.6.9. We could actually name tasks now before in 6.1, and before that we could not do that. And this proposal introduces a way to provide a name for the task. And this is helpful for debugging, for example, or if you have like similar tasks, you could like declare them. And also it uses a string interpolation. You can like place a string there, interpolate it. Global actor isolated conformances. This one is a big one, and it addresses some concurrency problem that allows types isolated to a global actor, like the main actor, to conform to protocols in a way that maintains their isolation guarantees. In the current world, we have a type which is isolated to a global actor, like main actor, for example, and it faces challenges when we try to conform to other protocols. For example, if you want to add the equatable protocol to a main actor class, you'd get an error like main actor isolated static function equals cannot satisfy non-isolated requirement. And this proposal fixes the problem. While the protocol requirements are typically non-isolated, but the types implementation is isolated to the main actor, And this proposal introduced the isolated conformance, which allows a type to specify that its conformance to a protocol is also isolated to the same actor. So whenever we have the another protocol here, like equatable, we could say at main actor equatable, and this will guarantee like the equal it will run on the same actor that my class is currently does. This ensures like type safety. The compiler can statically verify that the conformance is only used within the correct isolation domain. There's no need to do it on runtime. We had a previous workarounds with non-isolated and main actor that assume isolated. We don't need to use them anymore. It also reduces the code for it, and yeah, I think it's way nicer. Just use this at main actor to the protocol, and that's it. We don't need to rely on something else. The existing code should not be affected unless types are explicitly marked with isolated conformances, and the rules are pretty much the same. Cool, and that's it for Swift 6.2, the additions that were added. We also have a few proposals which will be added in Swift previous versions. We are accepted right now, but have not been yet implemented. Explicit specialization, and this proposal introduces a new attribute called @specialize and allows us to create specialized versions of generic functions for specific types. This happens, the Swift compiler can automatically specialize that generic function at compile time, creating optimized versions for specific types. When you call that with a concrete type, the compiler can generate a highly optimized version, but this optimization breaks down in two scenarios. And with this new attribute, it helps a bit the compiler when it generates the functions. The example is with this in the proposal with the sequence where you have like the binary integer for elements, and it's mentioning that the compiler now has no way of knowing that the type is at the call site, neither the sequence type nor the element type, and it executes an unspecified code, which is like not that optimal, but with this addition you could like create here with the attribute, allowing the function to say, hey, this is like a function which specializes in something, and here you have like working with integers and so on, even though the element that you declare for the sequence should be a generic binary integer. A specialized version of that will generate this in the same way you have to do it at the call site. This is like very helpful for a compiler, and like improves the performance there. Right. Next one, run non-isolated async functions on the colors actor by default. It has been accepted with modification. The proposal is 461. It starts with a nice introduction. Swift's general philosophy is to prioritize safety and ease of use over performance. As long as the code is safe and you like is easy to use, then we don't care that much on the performance. In the current behavior, this proposal is important because it changes the way the non-isolated async function behave. It's like in the current world, the non-isolated async functions have a confusing behavior. They are inconsistent. Well, like non-isolated sync functions run on the colors actor. The non-isolated async functions switch off, always switch off from the actor. And this can create some weird behavior. So you'd create some kind of isolation for that async function, like isolated on some actor, if you like you're hardcore into Swift concurrency. And with this proposal, you have a way to that the language changes this behavior. Non-isolated async functions will now run on the colors actor by default. Very important to remember. And we gain two new attributes: non-isolated non-sending, which is explicitly marking a function to run the colors actor, and also at concurrent. And this function add concurrent will always switch off an actor to run using the add concurrent attribute. Yeah, this provides like a better safety, and you have explicit control for how you would use your async functions. Increases the safety, of course, and you can like do whatever you want for in this scenario. All right, so you have add concurrent if you want to keep the same behavior, and you'd like use it in prefixing the function. It will run off the actor if you use add concurrent, but if you don't, it will keep the actor there. This is a significant improvement in Swift's concurrency model, making it more intuitive and safer to use while maintaining the flexibility to control. So with these new keywords, you have the complete control on how you would like to execute that particular async function. All right. UTF-8 span, safe UTF processing over contiguous byte. Right, UTF-8 span, I think it's in Swift proposal 464, has been accepted, and it introduces a new type called UTF-8 span, and it provides an efficient and safe Unicode processing over the contiguous memory. It tries to fix an inefficient way when we create strings. When we need to process those UTF-8 bytes from in Swift, you need to create a string instance, which is like allocating a new memory. You copy all the bytes, you use reference counting, and you need to map the string index, and this doubles down the memory. It also have some memory constraints. String may not be available in tightly constrained platforms, not just iOS. And you have a performance overhead. Caching string instances, it doubles the memory basically, and you'd recreate them on the fly. With this new type, UTF-8 span, you have a non-escapable type that provides a safe access to UTF-8 in this like contiguous memory, ensuring like a memory safety. Performance-wise, you don't need to allocate it. Yeah, there's no reference counting, and you have direct byte access there. So it's very performant, very good from a memory efficient way, and you can use it in other platforms. Primitive standard library. So we have some additions from non-escapable. In the proposal, which is 465, we have a related section where we are linked to the copyable and span and non-escapable types and so on, which is like could capture links here. This proposal extends the Swift's standard library to better support the non-escapable types. It's incremental, it builds on the non-escapable proposal that we spoke already. And now we're going to allow optional and result to hold instances of non-escapable types and continue the work of adding support for non-copyable and non-escapable types throughout the Swift standard library. So through all of those things in the Swift standard library, now adding support for non-escapability. This proposal is focusing on optional and result types, and it will allow optional to wrap non-escapable types, becoming conditionally escapable, and do the same for result types, where the success case will hold the non-escapable item and do some other things to the memory. Right, so we're going to have non-escapable optionals now. Empty optionals of non-escapable types are still technically non-escapable, but they aren't inherently constrained to any particular context. So empty optionals are born with immortal or static lifetimes. They have no lifetime dependencies. All right, so we would like to make them part of the scope. And in the Swift proposal, we have a detailed design, what's happening, plenty of examples, so go check it out. Swift 467, it adds the mutable span and the mutable row span. Delegate mutations. Span, we would be able to see that zone of memory, but now with mutable. We have a new type to delegate, remember, delegate mutations over that zone of memory. And it builds on top of the span and row span types. In current world, you have unsafe ways to modify the zone of memory with functions like with unsafe mutable buffer pointer or with contiguous mutable storage if available. And these are, sorry, they rely on unsafe type. They are not suitable for security conscious, for security related applications. And they use a closure-based API, which is difficult to compose and use in other functions. We have new types, the mutable row span, mutable span, which is for typed memory mutations. You have here an example in the proposal. You have get probably an array, you modify the mutable span, and then you consume and access where you like create that thing. And mutable row span is for untyped memory mutations such as encoding. A Swift proposal 468, hashable conformance for sync throwing stream continuation. It's a simple addition to hashable protocol to work with continuation. It will simplify working with multiple streams. You have the async sequence or async stream in the language. And if you work with multiple async streams, you'll have to store multiple continuations. You have to handle termination callbacks, and you remove specific continuations, and you do like a lot of things. Your code will probably not look that great. And this proposal will add conformance to hashable to work directly with the async stream continuation. You could store those continuations in a set, for example, or compare continuations efficiently. And the final proposal I want to talk today is clock epochs as part of 473. We have in a previous proposal we have new concrete clock types: suspending clock, continuous clock, and UTC clock. While not all clocks have a meaningful concept, suspending clock and continuous clock do and have access to it can be very useful. Right, so we have a lot of clocks in Swift, but now we have another one. With this proposal, we add the system epoch properties to the Swift clock types, and you would provide access to their reference points. We have a new property called, and this will expose their system-specific reference points. This will allow us to measure time relative to the system's epoch, compare durations across processes, interface with code in other languages, and so on, which is quite nice. Right, thank you so much for listening, and see you next time. Bye. Greatest story ever told in rhyme.